This lecture we will discuss about three-state gate. Up to now, whatever gate you have studied has two state, that is high or low, that is also known as logical high or logical low, or in a physical world that may be 3.3 volt or 5 volt or maybe 12 volt, and a ground, usually ground. In some cases that is also a negative voltage. Okay, so we have two state logically, that is high or low. But in three-state gate, along with a logical high and logical low, we also has a high impedance state. This is the third state of a three-state gate, and that's exactly why we call it a three-state gate. Okay, so we have the figure of a three-state gate here. It has one input, one output. This is just like a buffer. It is just like a buffer. It doesn't do any kind of operation here. It's just kind of a switch which has three particular state. We also have a control input here. Now according to this control input, the buffer or the three-state gate behaves. If the control signal is high, we will see the output will follow the input. If the input is, that is A, is high, it will output will also be high with a negligible propagation delay, we would say. If the output input is low, then the output would also be low. But in case of C, the control signal is 0 or low. What happens is your output is high impedance. We call it high impedance. Or you can also see that in a way of, like, this is an open circuit now. Okay, in case of previous cases, like, it is always connected. If the input is 5 volt, then the output is 5 volt. If the input is grounded, then the output is grounded. But that is the output is connected to the input physically. But in case of three-state gate, if the control input is 0, then there is an open circuit there. Even the noise in the input cannot affect the output. Okay, so that's exactly the purpose of this three-state gate. It gives you much more better noise immunity along with proper isolation. Okay, if you're dealing with digital signal, there is interference, and external interference can affect digital circuits. So that's why this type of procedure is followed to to mitigate that problem. So we will see a simple example here which uses this three-state gate. Now by the looking at the figure, you can say this is a 4x1 multiplexer. You can deduce that it has 4 input, 1 output, and also you have select lines, and select lines is 2, so that's why we can say this is a multiplexer. Now we have used a decoder here and 4 three-state gate. These are all three-state gate. It has input and output. It propagates the input to the output, and at the output, you see, you can use an OR gate here. You can use an OR gate here, but I have just wired all together to represent that all wires are connected together and they are connected to the output. Okay, logically what you used, normally an OR gate, but in this particular case you can actually wire all the wires at a single point. That is, physically you don't need to use an OR gate. I will explain why that. So I will explain the operation first. You see, input is connected to the output through this three-state gate. Whenever your select line is selecting, your decoder here is used to select any one of this three-state gate. If 0 0 is the input, you can say that your three-state gate 1 is activated, whereas other three-state gates are deactivated or in high impedance state, or you can say those are open circuit. So whatever the input at that particular stage will not affect the output. Only I0 will affect the output. If 0 1 is there, because decoder only one output is active at a single time, whereas others are going to be 0. If 0 1 is the input combination or select line, S0 and S1, your output would be from the 3-state gate 2, whereas others are open circuited. Any interference or signal will not affect the output, and those are physically connected. Now that's the reason we can connect physically all the outputs of this 3-state gate together at a single point without using any OR gate.